This is Chemistry 108 at York College. It's March 12th, 2015. We will continue on Chapter 4. Okay, so let's review some of the stuff that we did last time. So let's look at some compounds. Silver chloride, soluble or insoluble? Soluble or insoluble? Insoluble. Who thinks it's insoluble? Who thinks it's soluble? Who doesn't think at all? Okay. Say again? It's insoluble. Why is it insoluble?
Because it has a Ag and that's the exception.
So chlorides, what does the rule say? The rule says chlorides are all soluble except for silver, mercury, lead, right? Okay, so let's say Na2SO4. What's that called? Sodium what? Sulfate. Sodium sulfate. Soluble or insoluble? Soluble. Why is it soluble? Sulfate, kind of. But the better rule is...
Is it because it's ionic and Na is soluble?
Right, so all of your Na salts, all of your sodium salts, all of them, at least on this level in Chem 108, are going to be soluble. Most of your sulfates are going to be soluble, with some exceptions. Okay, let's see, what else? Aluminum nitrate, soluble or insoluble? Who thinks it's soluble? Who thinks it's insoluble? Okay, so that's like 2 to 2 in a class of about 55. Okay, what's the key ion here? Nitrate. Nitrates are always soluble, right? Just like sodium and potassium and the group 1 elements are always soluble. Nitrate is always soluble in 108 with no exceptions. Okay, so lead 2 sulfate, right? PbSO4. Insoluble. Lead is one of the sulfates are soluble with lead as one of the exceptions. Okay, so let's keep that in mind and let's do a reaction. Na2. Oh, okay, so let's do this from the very beginning, because you might see something like this on your exam. It's quite possible. Let's say lead 2 nitrate reacts with, I forgot. Okay, potassium sulfate. What are we going to do? We're going to say 1, write a balanced molecular reaction or complete or molecular equation. It means just a balanced, regular, plain old balanced equation with states. Circle the precipitate. Precipitate. Right. An ionic equation, what we could call a complete ionic equation, or write the equation for the complete ionic reaction. again, with states, and write the net ionic equation, or the equation that defines the net ionic reaction with states, and identify what? Spectator ions. Very good. You could actually write your own test. I mean, the questions are kind of standard. Okay, so the first thing you need to do is know what lead 2 nitrate is. So lead 2 means we have Pb what charge? Plus 2, right? So we're going to have Pb2 plus, and nitrate, you need to know what nitrate is. NO3 and what charge? Minus. So we're going to do our crossing over, and we're going to get Pb NO3 2. Is that soluble or insoluble? Soluble. Why is that? Because of nitrate. Right, nitrate salts are all soluble, so we're going to write AQ. Plus potassium sulfate. Potassium is K plus, the potassium ion, and sulfate is SO4 2 minus. So we're going to do our crossing over. K2SO4. Soluble or insoluble? Why is it soluble? Mostly because of the K, right? Because, I mean, sulfate has exceptions. K is not one of the exceptions. Remember, your group 1, lithium, sodium, potassium, rubidium, cesium, all soluble all the time. And that, I'm going to run out of space here. I'm going to write it a little smaller. Plus K2SO4 gives you what? PbSO4. You need to think about do your crossing over when you do your exchange. Right, so Pb2 plus SO4 2 minus. So you're going to get 2 and 2, and that's going to reduce to 1 and 1. So it is indeed PbSO4. And that's going to be, what did we say this was? Solid, insoluble, plus KNO3, and that's 1 and 1, the charges. And that's going to be aqueous. This is one of the most soluble salts ever. Are we balanced? No, we are not. So we're going to have to balance this. When you're looking at exchange reactions, you can think of your nitrates as units, right? You can think of your sulfates as units. You don't have to balance the sulfur and then the oxygens. You can just think of that as a nitrate. So we've got 2 nitrates, 2 potassiums. We're going to need 2 potassiums and 2 nitrates, and I think we're done. Is that correct? Yes, we're done. So we got 1 lead, 1 lead, 1 sulfate, 2 potassiums, and 2 nitrates. Questions so far? Okay, so we wrote a balanced molecular equation with states, and we circled we circled the precipitate is the solid. So these different types of equations, the molecular equation, the complete ionic equation, the net ionic equation, they're all in some sense real or correct, but they're describing different aspects of the reaction. Right? Here, if you were trying to set up this reaction in the lab, you would go and find a bottle of lead 2 nitrate on the shelf, and you would find a bottle of potassium sulfate on the shelf, right? And you would make solutions and you would mix them. But once you've made solutions, if it's aqueous, it's no longer PbNO3 and it's no longer lead nitrate, because when ionic compounds dissolve, what happens to them? They disassociate, or they become the component ions, right? And so because they're charged, what kind of solution is it? Electrolyte or non-electrolyte? Electrolyte. And so if you stick the shiny thing in with the bulb, right, it's going to light up. So lead nitrate, once you put it into aqueous solution, it becomes, 1 unit of lead nitrate becomes 1 unit of aqueous lead ion plus 2 units of nitrate. Right, this is from the lead nitrate. What about the K2SO4? It becomes how many Ks? 2 Ks, 2 potassium plus 1 SO4. And that gives you PbSO4. If it's solid, it's solid. Do solids dissociate? No. So the solid is a solid. So yields PbSO4 solid plus what? Plus 2K aqueous plus 2 NO3 minus aqueous. From the point of view of the solution, what are the components of the solution? This is correct. Right? From the point of view of what you're measuring out, this is correct. Or this is more, you would say, accurate. Right? This is but from the point of view of what's actually going on, what's changing? Well, the spectator ions don't change at all, right? The spectator ions just hang out and do nothing. So to identify the spectator ions, we're going to look on the left and look on the right, and see what hasn't changed, what is the same. And so what is the same on the left and the right here? The NO3 is the same, right? You have 2 NO3s and the 2 Ks, 2K plus. So those are the spectator ions. Right, the spectator ions don't change. So from the point of the view of what's actually reacting, what's changing, it's the net ionic reaction, which we would represent by everything that's left. That's the most accurate. So it would be Pb2 plus SO4 2 minus gives you PbSO4 solid. And so here's what we call the ionic equation, or the complete ionic equation, with the crossed out thing still intact, right? And then the net ionic equation is removing the spectator ions. And so the spectator ions are K plus and NO3 minus. No? Yes? Process it all. So look at this before I erase it. Yeah, got it? Good. Say that again? Yes. Yes, because that's what it is, right? It's not K. K by itself would indicate it's potassium metal, uncharged. Right? So K plus indicates it's an ion. sodium, the solution of, okay, we should be aqueous solutions of sodium hydroxide and iron 2 nitrate are mixed. Do the same thing. Except this time, I'm not going to do it. You're going to put your heads together with your friend gently and give it a try. Let's do it. Okay, so what is sodium hydroxide? NaOH. Plus 1 minus 1. That's going to be aqueous because of the sodium. Fe. And parentheses 2. Arrow.
And then you get Na.
Yeah.
Open and close parentheses with NO3. And then you put 2 left to add.
No 2 here. What do we have to for each new species, each product that we get, we have to do the crossing over again. Right? So Na is plus 1, NO3 is minus 1. So it's going to be 1 and 1. This 2 here has got to get taken care of when we balance the equation, right? Not when we do the crossing over, not when we do the switching. Right? So we get NaNO3, that's sodium, which is soluble, nitrate, which is soluble. FeOH, right, because the metal always goes first. And the Fe is still iron 2. OH is minus 1. 2. Fe parentheses OH 2. Iron hydroxide is insoluble. So that's going to be solid. And so we got to balance. I think we got to do this and this. We're happy? Okay, so that's our complete. This is our precipitate. It's the solid. And so we're going to write our complete ionic reaction now, which starts as 2Na plus, or plus 1, aqueous, plus 2OH minus, aqueous. The 2 covers this whole thing. Right, so there's 2 sodiums, 2 hydroxides, plus Fe2 plus NO3 minus. 2 of them, because we've got this, which covers the whole thing. So 2 NO3 minus. And that yields 2 Na plus, aqueous, 2 NO3 minus, aqueous, plus FeOH2, because the solid doesn't dissociate. It's a solid, right? It's a solid ionic compound. The ions are together when it's solid. Okay, so now we're going to identify our spectator ions, Na, and Na, and NO3, and NO3. Those are our spectator ions. So the net ionic reaction is going to be 2OH minus, are we happy? Good. Can you do this? Good. It will be on your exam. Maybe not this exact question, but not right now. Oh, you mean On Blackboard? Yeah, it's there. I just put it on this morning. All right, so let's think about acid-base reactions. Acid-base reactions are another class of metathesis reaction, another class of exchange reaction. If you remember back from naming compounds, what is an acid? So right now an acid is a compound that produces a hydrogen. Right, H+. Hydrogen ion. So something like HCl can give us H plus Cl minus. And when you take Chem 2, you'll learn, and then when you take organic, you'll learn lots of different ways of looking at acids. Right now we're just going to look at this one. Right? So this is what's called an Arrhenius acid after, Dr. Arrhenius, who was studying acids in this way. And the base, so acids produce H+ in aqueous solution. So that's going to be aqueous, and that's going to be aqueous. And an Arrhenius base is going to produce hydroxide. So something like NaOH, which we saw above, dissociates to produce Na plus OH minus. And so we have mostly what we're going to deal with in this class are what we call strong acids and strong bases. And so strong acids, there's a few of them, and you kind of need to know what they are, and it's pretty easy to know what they are. HCl, HBr, HI. So if you remember from your naming compounds, that's hydrochloric, hydrobromic, and hydroiodic acid. HNO3, H2SO4, HClO3, HClO4. Not too bad, right? Well, these are where? These are all in a row, right? HCl, HBr, HI in group 7, right? Then you have your oxychloroacids, chloric and perchloric acids. And then these two you've already dealt with in lab probably, right? Nitric acid and sulfuric acid. That's all. So your strong bases, at least on this level, are going to be your soluble hydroxides as well as oxides, nitrides, and hydrides. So where does that come from? So the hydroxides are pretty clear, right? If it's a soluble hydroxide, it produces OH minus. But what about oxides? So if you have an oxide, let's say you have sodium oxide, right? When that dissolves, what's that going to give you? That's going to give you Na2O, right? So 2Na plus O2 minus. The O2 minus then goes and reacts with the water because they're aqueous solutions, so there's lots of water around, right? And it's going to give you OH minus plus another OH minus, or 2 OH minus. So in other words, O2 minus, charge of -2, no hydrogens, and an oxygen. Water also has an oxygen, 2 hydrogens, no charge. 1 H plus goes from here to here. Right? And so when this guy loses an H plus, it becomes OH minus. And when this guy gains an H plus, it becomes OH minus. And so what happened? You produced hydroxide. Something similar happens for nitride, right? If we did, N3 minus, and we react that now with 3H2O, what do we get? We get NH3 plus 3OH minus. And for hydride, H minus plus H2O, that's liquid, right? Nope, H2O is not aqueous, H2O is liquid. That's going to give us H plus H minus is going to be H2 gas, right? H2 is hydrogen gas, plus OH minus. And so those are going to be your strong bases, right? Hydroxide, oxides, nitrides, and hydrides. We're just going to talk about this real briefly because you're going to learn this, lots and lots once you get to Chem 2, if your program, makes you take it, or if you just like chemistry a lot. What? You're allowed to just like chemistry a lot. A weak acid is going to be something like HF, hydrofluoric acid. Notice it's not on that list up there. Basically anything that's not there at this point we'll consider a weak acid. We typically draw a double-headed arrow here. And what this double-headed arrow means is it reacts, but it doesn't all react. Right? The HF becomes H plus and F minus, but not all of it does. Or another way to look at it is it becomes HF, H plus plus F minus, and then some of it goes back and becomes HF again. So what's going to be in a solution of HF? There's going to be HF and H plus and F minus. Whereas in a solution of HCl, this is all gone. Right? This has reacted entirely, and all you have left is the H plus and Cl minus. You have no HCl left. And that's what the arrow means, right? The single-headed arrow means. What the double-headed arrow means is you got this and you got this, but you still got some of this, and that's what makes it weak, right? If you have, 1 mole of HF, you don't get a mole of H plus. Whereas if you have a mole of HCl, you get a mole of H plus. Weak bases are typified by, or exemplified by, something like ammonia. A lot of these N-containing compounds. And what's going to happen is ammonia in water reacts to give you, any ideas? NH4, but you know something about NH4, right, from chapter 1 or 2. NH4 has something on it, a plus. It's called the ammonium cation. And what's left? OH minus. except this process is also controlled by a double-headed arrow. And so in this solution you have ammonia, ammonium, and hydroxide. So you don't have just, in this case, there's no more NaOH, right? It's a soluble ionic compound. Soluble ionic compounds, you learned, dissociate completely, right, into the cation and the anion. Here you have some of it going to NH4 plus, some of it going to OH minus, but some of it staying. And so that's what makes it weak. Okay, so that's the kind of the background we're going to need to think about acid-base reactions. So what's an acid-base reaction, or a neutralization reaction? A neutralization reaction is a type of exchange reaction that occurs between an acid and a base. So typically, what are we going to see? We're going to see something like HCl, which is an acid, plus NaOH, which is a base. And what are our products going to look like? HOH. Except what's HOH? H2O, right? There's two H's. H2O plus NaOH, aqueous. No, not NaOH, I lied. NaCl, aqueous. Sorry, say it again? And salt. Yeah, and so you have an acid plus a base gives you water and what's typically called a salt, ionic compound. NaCl we call salt as like table salt, but it doesn't have to be NaCl if it's not HCl and NaOH, right? We could have something like this.
Why won't the NaCl be a solid then?
Because the solubilities rules say that NaCl is soluble. So let's say we had HNO3 plus BaOH2. That's going to give us what? H2O and Ba, not quite. Ba is 2 plus. NO3 is minus. You're going to cross, right? So it's going to be BaNO3 2. That's going to be aqueous because it's a nitrate. And we're going to have to balance. This one we're going to have to balance, I think. And so we're going to need 2 of these to balance the nitrates. And that's it, right? Because we have 2 H's, 2 H's, 2 nitrates, 2 nitrates, 1 barium, 1 barium, 2 OH's. So where did that come from? Yeah, okay, so maybe we need something different. Did we do everything right here? Okay. Oh, yeah, okay, so we need 2 of these. Because we have H's from here and from here, yeah. So that's going to work, right? 4 H's, 1, 2, 3, 4, 2 O's, 2 O's. Yeah, that works. All right, so Before we take a break, we're going to do a problem, right? Because I don't want you to forget this. I want you to do a problem, and so you get it. It's not that different from the precipitation reactions. So let's say perchloric acid, aqueous, right? Aqueous perchloric acid reacts with aqueous potassium hydroxide. And so we're going to do the same thing. We're going to write a balanced molecular equation, write a balanced plain old equation. We're going to write a complete and net ionic equations and identify the spectator ions. Okay, so perchloric acid, that's going to be HClO4. Remember, ClO3 is chlorate, ClO4 is perchlorate, so this is perchloric acid plus potassium hydroxide, KOH. And what are your products going to be? What ClO4? KClO4. So this is +1, this is -1, plus H2O. And everything here is kind of balanced, right? Because all the charges here are 1, 1, 1, 1. So everything's balanced. H2O is liquid. Very good. So for our complete ionic equation, it's going to be strong acid, right? So strong acids dissociate completely. So we're going to get H plus ClO4 minus plus K plus OH minus gives you K plus aqueous plus ClO4 minus aqueous plus H2O liquid. Right? This is kind of like your precipitate. It doesn't appreciably dissociate. And so what are your spectators? Your spectators are potassium and chlorate, potassium and chlorate. And your net is going to be H plus OH minus gives you H2O liquid. Take 10 minutes. Okay. Hi. Let's do some more chemistry. Okay, so we're ready to go? Yeah. All right, so some acids are going to be like, say, sulfuric acid. Sulfuric acid has 2 H pluses, right, or 2 H's. Sorry? Oh. And so when you have a case like this is what's called a polyprotic acid, right? A polyprotic acid means there's more than one H plus, right? And so in the case of having 2, it's called a diprotic acid. And in the case of polyprotic acids, the H pluses come off one at a time. And so you're going to get H gives you H plus HSO4 minus. Do you remember what this ion is called? Something sulfate? Hydrogen sulfate? Yep. And then, but look at this. This also has an H on it, right? And it can lose that H. So then it can undergo a second reaction to give you another H plus SO4 2 minus. Except these guys in this class, the second ionization and beyond, some of them are going to have a third ionization, are all going to represent weak acid ionizations. And so this is going to be a double-headed arrow. Something like H3PO4 phosphoric acid, that's what's called a triprotic acid. That's going to give you H plus H2PO4 minus. That's dihydrogen phosphate, right? That itself is a polyprotic acid, so that can give you H2. Before we get there, H3PO4 is not part of our strong acids, right? So the first one here already is a double-headed arrow because it's a weak acid. And then H2PO4 can further dissociate to give you H plus HPO4 2 minus, and so on, right? So HPO4 2 minus can dissociate to give you another H plus PO4 3 minus, which is your phosphate. And so this is triprotic, this is diprotic. If you're a strong acid, it's only the first reaction which is a strong acid reaction. The following ones are going to be weak acids. In this class, pretty much all we're going to deal with, we need to be able to identify these polyprotic acids. But when we do reactions like this, we're just going to consider the first H+. Okay, so moving on, we need to consider, kind of put everything together, right? So we learned in chapter 3, we learned about moles, grams, reactions. Here we have more reactions. We have some specific kinds of reactions. Some of you asked back in chapter 3, are we going to have to know if you mix this and that, what are you going to get? I said most of the time no, except when yes, right? And so now you know what the when yes is. You need to be able to get your precipitation products, get your acid-base neutralization reactions, and then now we're going to start doing calculations. And so remember what calculations, or what solutions are. Right, solutions, in a solution, you have some solvent, right? That's in an aqueous solution, that's water, right? And you're going to have your solute. And that's going to be your salt or your sugar or your acid or whatever. What's a good unit to measure solvent in? Water. Liters. Volume, right? And what's a good unit to measure solute in? Either grams or moles, right? And so when you put those two things together, you get concentration. And concentration is a measure of how much stuff you have in a certain volume. Right? And so we don't necessarily know what these things are, but if you have two containers that are approximately the same size, which one has a higher concentration of solute, this one or this one? The left one, right? This one has more stuff in the same volume. Okay, so molar concentration is going to be moles per liter. How many moles of solute you have in a liter of your solution? And this can be abbreviated capital M. Has to be big, right? Because small m means different, something else, meters, right? You can also have mass concentration, right? Things like grams per liter, grams per milliliter, milligrams per milliliter. Those are all things that can be used, but we're going to focus in on this one, right? Molar concentration is moles per liter. Okay, so let's do kind of a silly problem here. Let's say you have 3 moles of sodium chloride in water, and the resulting solution has a volume of 2.2, let's say 2.0 liters. Let's call this 3.0 moles and 2.0 liters. What is the molar concentration? Well, the molar concentration, how are you going to find that? You're going to take the moles, you're going to divide it by the liters. So it's going to be 3.0 moles divided by 2.0 liters, and that's going to give you 1.5. And the unit on this, you can write it one of 2 ways. You can just leave it like this and write 1.5 moles per liter, or you can take the moles per liter and replace it by this, and we say this molar. That's the name of the unit. So it would be 1.5 capital big uppercase M. Yep. If we're going to call it molar, then it needs to be in liters. Yeah. I mean, there's ways to describe, you could describe it in milliliters, but then you wouldn't call it molar. It would just, moles per milliliter or something. Okay. So here's a very common kind of thing that people would do. Right? If you took when it's becoming a little harder to find this, but you would take, when I was a kid, we would take like a can with concentrated like orange juice, right? And we would dump the can into a big pitcher, right? And so you'd have this lump of like half frozen orange juice in the bottom, and you would add water, right, to fill up the pitcher and mix. What's that called? Making orange juice, right? But what's that process called? It's dilution. You're taking something that has a high concentration, in this case it's a high concentration of orange juice, to something that has a lower concentration of orange juice by adding some water, right? And so that's dilution, and you'll see lots and lots of different applications of this. So let's say, right, orange juice obviously is a heterogeneous mixture. There's lots of different types of substances in it. But let's say we're tracking the orange, the sugar in the orange juice, right? The sugar is a compound that we can kind of measure. So if you have, let's say, I don't know, 100 grams of sugar here, and you dump the whole can, so all the sugar goes in here, and you add water, how much sugar do you have here now? Still 100 grams, right? You didn't change, you didn't add any sugar, all you added was water. So if you had 1.5 moles of sugar here, and you dumped the can into here and you added water, how much would you have? 1.5 moles, right? You're not adding, right, if you're not adding any sugar. In other words, if I have something like this, right, I have 3 squares of whatever, and then I add water. I dilute the solution by adding water up to here. I still have 3 squares, right? They're probably, I didn't change that. All I changed is the volume. And when I changed the volume, I changed the concentration, but not the total moles. So if I'm doing a dilution, what does that mean? That means moles 1, right, before, equals moles 2 after, right? Let's go back here, right? If I have moles divided by liter equals molar concentration, I can solve for moles, right? Because moles equals moles. So moles, if I multiply both sides by L, right? What happens here? L and L cancel. And here I get moles times liters. So what is molar times liters? So this is molar concentration, and this is volume, equals moles, right? So if I take this and kind of plug it into here, what am I going to get? I'm going to have concentration 1 times volume 1 equals concentration 2 times volume 2, because the moles of 1 equals concentration of 1 times the volume of 1. And the moles 2 equals concentration of 2 times the volume of 2. And if I'm doing a dilution, they're equal. I didn't change the total number of moles, right? You just told me that. So does that make sense? Yeah. So this is kind of the central equation that you're going to use when you're thinking about dilutions. You may also see it written M1V1 equals M2V2 for molar times volume equals molar times volume. It's really referring to the same thing. So if I take this solution here, right, it has a concentration of 1.5 molar. It's 3 moles in 2 liters. Right, so let's say I have a container here, and it's up to here, right? This is 2 liters. 1, 2, 3, 4, 5. And then I add 1, 2, 3, 4, 5. And I add water, right, it starts 3 moles into 2 liters. I add water, so now it's all the way up to the 5. What's the new concentration? Right, so I take my 3 moles in 2 liters, and then I bring the volume to 5 liters. What is the final concentration in molar? What am I going to do? I'm going to use that. Let's say C1 V1 equals C2 V2. What's C1? This, 1.5, right? That's what I'm starting with. 1.5. What's V1? 2.0. And what's C2? We don't know. And what's V2? 5.0. So when we do the math, we get C2 equals 1.5 times 2.0 over 5.0. And so let's put in some units here, right? This is molar, this is liters. This is going to be molar, this is going to be liters, right? So 1.5 molar times 2.0 liters divided by 5.0 liters. Liters and liters cancel. What unit I'm left with is molar. And I'm going to get 0.60 molar. So C2 equals 0.60 molar.
But wouldn't it just be easier if you know the amount and you know how many moles are in it, you could just divide?
Essentially, that's what you did, right? This is the number of moles here, and you divided it by the new volume. That's correct. Okay. So that's one kind of calculation we might be looking at. We could also do okay, and so we can also do, but once we know stuff about molar, right, we can start doing calculations that have to do with our reactions, right? And so if we do something like this, so if we have, what was the first reaction we did with the lead? That was lead to nitrate, PbNO3 aqueous, plus, what was it? Potassium sulfate, K2SO4, aqueous, and that reacts to give us KNO3, aqueous, plus PbSO4. And we have to balance it, right? So what's, no, not aqueous, solid. Right, and what's our balance? We got 2, and that's it, right? Right, okay. So these concentrations can be difficult to measure. What's not difficult to measure is mass, right? Mass, you just take your stuff, you dry it down, and you put it on balance. Right, so if we find a mass here, then we can do what? We can use the molecular weight to find moles. Or if we have a mass, and if we have a mass in grams, so now I'm reaching back into chapter 3, right? If I have a mass in grams, I use the molar mass, I can find moles. I have a balanced equation. So if I have moles of this, I can find moles of that. Now, in chapter 3, once I found moles of this, I could reach back and find grams. Now I'm not going to reach back and find grams. I'm going to reach back, and given a volume and moles, what can I find? Concentration, molar concentration. So let's do this, yeah? Let's say I have 75 grams of PbSO4 are produced from the reaction of 1 liter of PbNO3. Let's not use 1, right? That's a bad number to use. Let's see, 0.25 liters of PbNO3 solution and excess K2SO4. Right? We don't want to do any kind of limiting reactants at this point. find, and I'm going to write this. These square brackets mean molar concentration. So PbNO3 2 means molar concentration of PbNO3 2. That's kind of a shortcut we use. Can we do this? Yes. I heard one person say yes. That's kind of encouraging. So what are we going to do? We're going to start with, we're going to make this map again, right? So grams of PbSO4. We're going to go from there to moles of PbSO4. Right. Whenever we go from one compound to another, like a reactant to a product or a product to a reactant, we're going to have to go through moles. What are we going to use to get from grams to moles? Molar mass of PbSO4. From moles of PbSO4, we're going to go to moles of PbNO3. PbNO3 2. To do that, what are we going to use? Mole ratio, coefficients. Once we have moles, and where do we want to go now? We want to go to molar concentration, which is big M, or moles per liter. Once we have moles, and we want to get to molar, what do we have to use? Sorry? Volume. Because once we get here, we have the moles. To get moles per liter, we have to use the volume. We can do this. Okay, so the first thing we need is the molar mass of PbNO3. And so, no, PbSO4. So Pb has an atomic weight of, let's look that up. It's kind of big, right? It's 207, is that right? 207.2? Yep, and so that's 207.2 times 1, right? And S is going to be 32.1, is that correct? 32.06? 06? 07. And O is going to be times 1 is going to be 15.9994 times 4. And that's going to be, does anyone have a molar mass for me? I meant that. Calculator. So it's going to be 15.9994. Sorry? Yeah, 63.997. I'm getting 6. Plus 32.07 plus 207.2. So we're going to get 7, 6, 16, 12, 10, 13, 9, 10, 303.3, right? Because we're going to cut off here. 303.3 grams per mole. We got our molar mass, right? So what are we going to do? We're going to say we start with 75 grams. I'm going to run into a wall here, so I'm going to write this down. 75 grams of PbSO4. I'm going to work backwards. I'm going to say 303.3 grams of PbSO4 per mole of PbSO4. When I do that, I'm going to get moles of PbSO4. That's the molar mass, right? What's next? What's next is the coefficients. In this case, it's just 1 and 1. I'm still going to write it out because my professor told me to. So 1 mole of PbSO4 gives me 1 mole of PbNO3 So now I'm going to get moles of PbNO3 and I'm not going to use the molar mass to get grams of PbNO3. What am I going to do? I'm going to use the volume to get moles per liter. So where am I going to put the liter? Top or bottom? Bottom, because it's going to be moles over liters. So I'm going to just put a 1 on top. And the liters is 0.25 liters. And when I do that out, I get, anybody faster than me? 75 divided by 303. And then to 2 significant figures, I'm limited here and here, I get 0.99 moles per liter, or 0.99 molar. Questions? Yeah.
How did you, the middle part where you go from the third parentheses?
This one? That's using the coefficients, right? In this case, it's just, there's a pretend 1 up here and a pretend 1 over here. Right. Oh, that's one of this. So this kind of, it's just an application of stoichiometry. Your book and a lot of books will break this kind of analysis out and call it gravimetric analysis. It's a common analytical experiment where you do a precipitation reaction, you get the mass of the precipitate to find out something about the reactants. You could imagine finding out the concentration of the reactants. You could imagine finding out something about a molecular weight, lots of different things. Okay, so here's another kind of reaction called a titration reaction. Right? So in a titration, typically what you're going to do is you're going to have one of your solutions in what's called a burette, a long thin tube that's marked. If you haven't used this in the lab yet, you will soon. And you have another one of your reactants in a flask. You know something about this, and you're trying to find out something about this. Or you know something about this, and you're trying to find something out about this. And your measurement important measurement here is going to be your volume. Right? You have generally what's going to happen is you have a known concentration. You find out a volume. Concentration times volume equals moles. Right? Concentration is moles per liter. Volume is, for example, liters. And what you get is moles. Once you have moles, I don't know if you noticed this yet. Once you have moles, you can do almost anything. Right? Once you have moles, you can find concentrations. You can find molecular weights. You can find number of molecules. You can find, if you have moles of one, you can get moles of the other. You can do anything once you find moles, almost. So let's look at our prototypical acid-base reaction. HCl aqueous plus NaOH aqueous gives me H2O liquid plus NaCl aqueous. And let's start with what I know. Okay, so what we know is, let's say this is your titrant, what you're titrating with. Let's say we know we have 0.25 molar solution, aqueous solution of NaOH, and we have what we have 65 milliliters of aqueous HCl. Right, so this is kind of what you start with. You have 65 milliliters of aqueous HCl. You don't know the concentration. You want to find out the concentration. So what you need to do is find out the molar concentration of HCl. And you're going to do that by titrating the sodium hydroxide solution in. You're going to add the sodium hydroxide little by little until you do something like you get a color change or something. You set up the reaction so that you can tell when the reaction is done. In other words, you can tell when the moles, what you want to do is when the moles of NaOH equal the moles of HCl, then you're done. You've reached what's called the equivalence point. You've finished the reaction, and now you can do your calculation. And let's say it takes us 25 milliliters of the NaOH solution to reach the equivalence point. Now we have basically everything we need, right? Moles of NaOH equals moles of HCl. That's kind of interesting now, isn't it? That sounds kind of like what? Something we saw about half an hour ago. Yeah, that sounds like moles of 1 equals moles of 2 for our dilutions, right? In our dilutions, we said before we add the water and after we add the water, we've got the same number of moles. So this is going to be equal to the concentration of base times the volume of base equals the concentration of acid times the volume of acid. And what's really nice about this is, as long as the volumes are the same, in this case we don't have to convert to liters because the millis are going to cancel out. So let's do this. Right, so we've got a concentration of base, which is concentration of base is 0.25 molar. The volume of base is 25 milliliters. The concentration of acid is, we don't know. And the concentration of base is, the volume of acid is 65 milliliters. So concentration of acid, which is what we're trying to find, is going to be 0.25 molar times 25 milliliters over 65 milliliters. The milliliters and milliliters canceled. So we don't have to, as long as it's the same, we don't have to convert to liters here. And we get (25 times 0.25 divided by 65 equals 0.096 molar acid of our acid, which is HCl. Questions here? Okay, so go home and do about 10,000 problems like this, right? Your ALEX is due on Monday, but beyond your ALEX, you'll probably want to do those practice problems in your book. There is also a, don't go anywhere yet. Don't go anywhere yet. Don't go anywhere yet. Don't go anywhere yet. There is also a review sheet on Blackboard. Do your problems first. I want to show you one more thing. Don't leave. Because we have about 2 minutes, and it's going to take me 2 minutes to show you. Let's go back to dilutions, right? In dilutions, we have this formula, right, that says C1V1 equals C2V2. There's one place where you need to be really careful, right? In the first question that we did, we said we had our initial volume was 2 liters, our final volume was 5 liters. Sometimes you'll get a question asked like this, right? You have 3.5 molar solution of whatever, solution of glucose, all right? And you start with, let's say 5.0 liters. Another 7.5 liters of water is added. Find the final concentration of the diluted solution. So what you're going to do is you're going to say, oh, I know that. That's a dilution. I'm going to do C1V1 equals C2V2. And C1 is 3.5 molar. And V1 is 5.0 liters. And C2 is, we don't know. And V2 is 7.5 liters. And you're going to get it wrong. Why is that? Because you added 7.5 liters, right? So you had 5, you added 7.5. So this is going to not be 7.5, it's going to be 7.5 plus 5.0 liters. And so when you do that, you're going to get 3. C2 equals 3.5 molar times 5.0 liters over 12.5 liters, right? 7.5 plus 5 is 12.5. And that's going to be your answer. Does someone have that? So why am I telling you that? I'm telling you that because when we put that on the exam, some of you will get it wrong. Some of you will say, Professor, you tried to trick me. I'm going to say, no, I didn't. I told you when you were trying to leave class early. 1.4 molar. Okay, now you can go.